Hello, everyone. My name is Neda Alzaben, and on behalf of my advisor, Dr. Ingalls, and myself, I would like to present for the ICACT 2021 conference a solution to an optimization problem. We present a solution to the end-to-end routing in SDN controllers using MaxFlow MinCut routing selection algorithm. To begin with the question, why end-to-end routing? We say that with the exponential growth of communication networks, along with the need to share information over it, some of which are in the form of video files that consume the network traffic, these files need to be transmitted from one end to another end using the same path. Therefore, end-to-end routing became critically important. Routing is the process of finding a communication path between two devices in the network to transfer information flows from one device to another. We define the problem as given: an arbitrary graph G with a set of vertices and a set of edges that connect those vertices, and a set of flows where each edge on the graph has a capacity C. That represents the maximum number of flows that can be transmitted at a time on that edge. And each flow is characterized by the number of packets it holds and a release time. Non-preemptively route all flows on graph G to optimize some objective function. The software-defined network is a network model that splits the network functionality into two separate planes: control plane and data plane. The control plane is placed in the SDN controller and the data plane is in the network switches. The controller is responsible of finding the routes for the network flows, since it holds a global view of the network. Then it loads the route into the network switches to forward the flow from its source to the destination. Shortest path algorithms are most widely used in end-to-end routing. However, they do not consider explicitly bottlenecks when routing, which results in poor performance in high-load networks. The shortest path-based algorithm considers the shortest distance path or the minimum hops. Bottlenecks in networks occur when a high traffic flow demands to be routed over a set of edges where the number of flows are exceeding the edge capacity, which leads to congestion at the edges. The shortest path finds the short path available and sends the traffic which most likely will meet in a specific path segment, which causes a bottleneck problem. Clearly, the routing algorithm that will resolve or at least minimize the occurrence of bottleneck problem has to consider congestion explicitly within its algorithm. Therefore, we use the shortest path algorithm as an evaluation base for ours. Moreover, routing on the World Wide Web has self-similar traffic, which tends to be heavy-tail distribution, file size, and that self-similarity affects the network performance. One common heavily tailed distribution is the Pareto distribution, which we adopt for our flow size distribution. We propose an algorithm that is based on the MaxFlow MinCut theory that was developed in the 1950s by Fulkerson and Shannon. It is a polynomial time algorithm, meaning the algorithm can solve a problem optimally in polynomial time, bounded by an upper bound equal to the number of edges times the maximum number of packet flows. The MFMC identifies the minimum number of edges with maximum flow capacity, such that if removed, it will partition the network in that the source node is disconnected from the destination. The flow routing process happens in two steps. The first step is selecting a flow from the flow set, then finding a route for that flow. Our algorithm is used for the second step of this process, finding a path. We utilize the MFMC process in partitioning the network by a recursive loop of cuts, where each cut contains a set of minimum number of edges. With their removal, the source and the destination are disconnected. The bandwidth of the path is defined as the minimum edge capacity in that path. Here we can see the code of how our algorithm works. The input values are an undirected network graph G and a flow F, and the output is a path for that flow. The function find path in graph first check if the source and destination of the flow are connected. If so, it will get the minimum edge cut set and then pick an edge E from the set. Then it appends that edge to the path list. If the selected edge contains both source and destination, it will return the path. Otherwise, it will set node E2 as the new source and node E1 as the new destination. Then recursively run the function on the two partition networks. This loop of partitioning continues until the path is constructed. In our MC suite of algorithms, we have 5 variations. Each algorithm is varying in the decision criteria it adopts for picking the edge from the cut set. We can see in the table that MC1 and MC2 select a random edge from the cut set. However, MC2 selects the edge that does not cause any cycles in the path. MC3 bases its selection on being part of a minimum hop path from the source to the destination. MC4 and MC5 are based on the available capacity of that edge, where MC4 selects the edges with minimum capacity, which is the most congested, and MC5 selects the one with the maximum capacity, which is the least congested. To illustrate how our algorithm works, we will take this example of finding a path from node S to node D using MC5. The algorithm finds that the maximum flow capacity that could be sent from node S to D is 4. Then it finds the minimum number of edges with that maximum capacity. Once the edges are cut, we pick from the cut set the edge with the maximum available capacity and save it as part of our path. After that, the end node of the picked edge becomes our new destination node. The cutting process loops again, and again the edge with the maximum capacity is picked. The process recursively loops until we construct our path that connects the source to the destination. The path from source to destination is found. Our network simulator is developed in Python, and it models an undirected graph using 2 network topology, mesh network and Barabasi-Albert network. Our mesh network is partial mesh because it gave us a distinctive difference in our objective functions compared to the fully connected mesh. And the Barabasi-Albert network, which adopts a concept of generating networks based on power law degree distribution, is generated using Network X library. The size of the network ranges from 10 to 50 nodes. For each generated network, we randomly set each edge capacity between 1 and 10. In general, a set of flows are randomly generated and simulate an online flows where clairvoyant is not enabled, and we non-preemptively route them over the network graph. Each flow is described with source node, destination node, release time, either identical or arbitrary, and flow size in either Gaussian or Pareto distribution. The simulation calculates as network optimization factors the mean wait time, which is the average delay rate, the mean slowdown, the maximum completion time, and the mean throughput. We evaluate our MC suite of algorithms compared to the traditional shortest path algorithms, considering minimum distance or minimum hops. In dynamic shortest path with minimum distance, we abbreviate it by DSP-MD. Dynamic shortest path with minimum hops, the DSP-MH. Also, we evaluate our algorithm to the least congested paths in dynamic shortest path inverted weights, DSP-invert, which is the maximum distance. In the next slides, we present and analyze the results of our simulation. All the objective functions in concern were calculated and analyzed and compared to the shortest path algorithms. For the objective function minimizing the mean wait time, regardless of network topology, we found that from the MFMC variations, only MC3 minimizes the mean wait time more than the DSP-MD, DSP-MH, and DSP-invert, on average by 18.4%, 11.7%, and 15.3% respectively. Moreover, we have found that the mean wait time is minimized with flows with Pareto size distribution more than flows with Gaussian size distribution by 20.6% and 16.1%. However, the other variations, MC1, MC2, MC4, and MC5, have increased the mean wait time over all DSPs on average by 16.4%. As an illustration, we give an example for routing in BA network with arbitrary release time, flows with Pareto size distribution. In the effort of minimizing the mean slowdown, we found that MC3 minimized it slightly more than all DSP algorithms on average by 6.1%. Moreover, we have found that the mean slowdown of MC3 compared to DSP-MD is minimized with flows with Pareto size distribution more than with the flows of Gaussian size distribution by 12% and 8.4% respectively. However, the other variations, MC1, MC2, MC4, and MC5, have increased the mean slowdown over all DSP on average by 5%, as illustrated in the figure, which is an example of routing in Barbasi-Albert network with arbitrary release time flows with Pareto size distribution. The flow routing process happens in two steps. The first step is selecting a flow from the flow set, then finding a route for that flow. Our algorithm is used for the second step of this process, finding a path. We utilize the MFMC process in partitioning the network by a recursive loop of cuts, where each cut contains a set of minimum number of edges. With their removal, the source and the destination are disconnected. The bandwidth of the path is defined as the minimum edge capacity in that path. In the effort of minimizing the maximum completion time, we found that MC3 minimizes it more than all DSP algorithms on average by 9.6%. Moreover, we have found that the maximum completion time for MC3 compared to DSP-MD is minimized with flows with Pareto size distribution more than with flows of Gaussian size distribution by 18.2% and 7.5% respectively. However, the other variations, MC1, 2, 4, and 5, have increased the maximum completion time over all DSP algorithms on average by 5.7. In the figure, we illustrate an example of routing in Barbasi-Albert network with arbitrary release time flows with Pareto size distribution. To maximize the mean throughput, we also found that MC3 maximized the mean throughput more than all DSP on average by 18.3%. Also, we have found that the mean throughput is maximized with flows with Pareto size distribution, same as with flows of Gaussian size distribution, by 18.6% and 17.2%. However, MC2 have not increased the mean throughput over the DSP. It has minimized it by 5.4. As for MC1, MC4, and 5, they maximize the mean throughput more than all DSPs on average by 9%. Here we present the results of our algorithms compared to the shortest path algorithms in maximizing the mean throughput. Positive values mean the MC algorithm is performing better. In this table, we can see that MC3 has performed better than the other variations. In all our simulations, we found that the constraint on flow release time, either arbitrary or identical, didn't have any impact on the evaluation on our objective functions. The min-cut algorithm that chooses its path based on minimum hop performed better in minimizing the mean wait time, minimizing the maximum completion time, and maximizing the mean throughput. However, it has insignificant changes in the mean slowdown. In conclusion, to optimize the end-to-end routing in software-defined network controllers, a routing algorithm should be used to maximize performance of the network. Our simulation showed that the novel Maxwell min-cut-based algorithm, MC3, with a decision based on minimum hops performed better compared to the traditional shortest path algorithm. Our algorithms are topology independent and flow release time independent. Since network bottlenecks causes performance degradation, our Maxwell min-cut-based algorithm explicitly identifies the bottlenecks through the min-cut edges, which holds the least available flows. And by choosing the edges on the shortest dynamic path, our algorithm is able to find path that yields significant improvement over the commonly used shortest path algorithms. The diversity of our MFMC suite of algorithm demonstrates that a shortest path approach, such as MC3, as opposed to a balanced or longer path approach, yields the best expected performance across the broad range network types and flow size distribution.